One of the most important relationships that we're going to be using with the C class is called the Parallel Axis Theorem. This allows us to figure out moments of inertia or angular inertias for many objects that aren't being rotated around their center of mass. It is used constantly. It is actually something you have to memorize because one of the C objectives is you will be able to state the Parallel Axis Theorem. And here is the Parallel Axis Theorem. Only I use this little star notation for, that represents the rotational axis for me, because as far as I know, there's no standard symbol for that, but this works pretty well. So what the parallel axis theorem is this. The moment of inertia, about some arbitrary axis which is parallel to the center of mass axis. It's got to be parallel to it. If it is parallel to it, then all you got to do is take the moment of inertia about the center of mass and add to it the mass of the object times d squared, where d is the distance from the center of mass axis to our new rotational axis, which is, it's got to be, and I'll put this right here, parallel to the CM axis. That's why it's called the parallel axis theorem. Here's an example. So let's say I've got a rod of mass m, and I'll make it mass m, and length L. The moment of inertia, and we'll derive this in the C class, about the center of mass. If you're rotating about this meter stick about its 50 centimeter mark, the difficulty of rotationally accelerating it, its moment of inertia, is 1/12 ml squared. What is the moment of inertia if you rotate it about a point 3/4 of the way down? In other words, here I am at 25 centimeters rotating it this way, accelerating it rotationally this way. Will that be more difficult or less difficult? Let's go ahead and figure this out. I about any parallel axis equals I about the center of mass plus md squared, and we got to figure out what this distance is. Now notice that this is halfway, that's 2/4. This is at 3/4 of L. So the distance between the center of mass right here, that's the CM, and the axis of rotation is 1/4 of L. So I'm going to take the I of the rod, and this you'd have to either calculate using calculus, or you might be given it. That would be 1/12 ml squared plus m times our d is 1/4 of L. It's the distance between the center of mass axis and our new rotational axis, 1/4 L squared. When we do that, we get 1/12 ml squared plus, this will give us 1/16 ml squared. Common denominator is 48, so this is going to be 4/48 ml squared plus, this will be 3/48 ml squared, and that gives us 7/48. I about that star axis is equal to 7/48 ml squared, which in fact is greater than 1/12 ml squared by a lot. Now, you could, if you just looked at this equation, you could tell me instantly, if you're not at the center of mass, the moment of inertia is going to be greater. Notice that this is a plus. You're always adding to it. In fact, the center of mass is going to be the lowest moment of inertia. If you're rotating about the center of mass, that's as low as it gets. Rotated about anywhere else, you're going to have to add this term, which means it'll be a greater moment of inertia if you're rotating about anywhere else besides the center of mass. In fact, the bigger that d is, the bigger that distance from the center of mass axis to your new axis is, the greater the moment of inertia. This parallel axis theorem is used constantly. It only works for axes which are parallel to an axis through the center of mass. You can't pick any axis. In other words, you can't say, okay, I'm going to go from here. Here's my axis goes right through this towards the camera here. You can't pick this axis spinning like that. That's not a parallel axis. That's in fact perpendicular.